Okay, let's discuss this problem here that you sent me. The most important thing when doing these is to look at each member separately. Do not look at this as a entire system because there's no way to do the problem if you do. So what I did here was I drew what this member would look like and try and draw a free body diagram of it. If I do, I would have 120 newtons acting here, and then I drew my x and y components at A, and again I'm just assuming what directions are going to go, and then I have this load here acting on it too, and we'll call that, let me see what that was called in the picture because it's hard to read. That member is called BC, so we can call this, we'll just label this as FBC, and we'll call this f of AY, and we'll call this f of AX. Okay, now according to the picture, this distance from here is 50 millimeters along this distance here, and this guy is running at a, so this is kind of a 60-degree angle here, I think it shows in the picture. Okay, so we'll go ahead and just write all our equations. Let's scroll down a little bit and look just at this member. What we can do is we can say we're going to sum the forces in the x direction and set them equal to 0, and we're going to sum the forces in the y direction and set them equal to 0. Now we should define what we mean by x and y because that's kind of arbitrary. So we're going to just draw an axis system like this. Anything that goes this direction obviously will be our x, and then this direction will be y. Alright, so when we sum our forces in the x direction, what we're going to get, and again you got to include the angles here, it tells you in the picture that this member is running, I believe, at a, it's not very good, it's supposed to be a straight line, 30 degrees here. So if that's the case, then this would make this angle right here 30 degrees. So I sum my forces in the x direction. All I would have would be, and I'm going to let what goes to the right be positive and what goes to the left negative, would be 120 right here times the sine of 30. Okay, and some of the textbooks, or they may actually have done this problem, a lot of times they'll do this. If this is 30, they'll make this degree 60, and they'll just say the cosine is 60. It's the same thing as sine of 30. That's going to give you the force, the x component of this going to the right, and the only other thing I have is FAX plus FAX is equal to 0. Now this only has a y component, so it does not create any x. So that's all you have, this force and the x component of this. Now we're going to sum the forces in the y direction, set them equal to 0. When I do that, I'll have minus FBC plus FAY minus 120 times the cosine of 30 is equal to 0. Right, and the only other thing we do, we could sum the moments at any point, and the best thing to do in one like this is take the point of A, because it's going to eliminate these two forces because they have no moment arm. Okay, when we do that, since we know the perpendicular distance from A to the 120, we could just use 500 as the moment arm. And anything that goes this direction will be considered negative. So I will get minus 120 times 500. And now what we have to do here is we have to look at the FBC, and we need to get the perpendicular distance. So FBC, and it's going to go back the other way. And we're going to multiply it by its distance, but we need the perpendicular distance. So we need this distance right here. Now if this angle is going to be running at 60 degrees, then we could say this angle here would be 30 degrees. So when the perpendicular distance from here to here be 50 times the cosine of 30. and set that equal to 0. All right. Now, if we look at this problem here, I have two unknowns here. I have one unknown here, so we can find FAX immediately. So we can say FAX is going to equal to minus 120 times the sine of 30 degrees. So I've just brought this to the other side. I'll grab my calculator. We'll run that real quick. 120 times the sine of 30 gives me 60 newtons. So FAX is going to equal to 60 newtons. Now I noticed in the book they showed it going, they made it positive, which I don't understand. It would have, let me draw this better. FAX would have to go back this direction here. And the reason being is because if you look in the picture, if this object's going this way, its x component is going to go to the right. FAX has got to go back the other way. It's not going to affect the answer any. So then we got that one. Now we're going to run this one right here. That's the only place else, because we can't run this one because we have two unknowns. So we can say FBC is equal to, we're going to move this to the other side, 120 times 500 all divided by 50 cosine 30. Run that number real quick. 120 times 500 divided by 50 times the cosine of 30 gives me around 1386. Newtons. Okay, that's FBC. Alright, and so we know what the force is coming down. That keeps this object from rotating. Alright, so now we know that, and now we can find the force FAY, because now we know this one. So we come back to this guy right here. We plug in minus 1386 plus FAY minus 120 cosine 30 is equal to 0. Solve for FAY. We're going to move everything to the right side. FAY is going to equal to 120 cosine 30 plus 1386. So we do that, plus 120 times cosine 30. That gives me 1490. Okay. Okay, just checking real quick. That was correct. So now we have all the components. So now we're ready to determine what the actual reactional force is. Because we know FAY is 1490. We know FAY is 60, or FAX is 60. So really what we have here is, if we draw a draw the vectors here, we know we have 1490 going up. We know we have 60 going back this way. So what we could really do would be, if we wanted to add the vectors, move this over, we could actually find out what the angle is if we needed to, because that's our resultant force. So we'll go ahead and label these. For this 1490 here, this is our 60 here. Get a different color. So then we could say force at A would equal to the square root of 1490 squared plus 60 squared. Run that number real quick. And that gives a value of about, so the 60 really it's so small it doesn't do much force. That gives us a reaction of about 1491 newtons. And honestly, you could find out what that angle is right here if you needed to by taking 1490 divided by 60 inverse tan would give us angle. Alright, so that's what the reaction force would be right at A. Alright, let me just look at the problem again. I think see if it needs anything else. Alright, I think we're pretty much there. So now we have the force at A. We know what the load would be at, let's go up here. We know what the load would be at FBC because we figured that earlier. Alright, and now the only other thing it wants us to do is determine what's taking place at D. Okay, so now I'm going to just do a rough sketch of what's taking place here. So I'm going to grab, see if I can grab some of this, I'll trim it when I get down here. We're going to take this, we're going to edit, copy that. We're going to come down to here. We'll paste that in. And I'm going to clean everything up a little bit so you can see that. Okay, so now if we want to draw a free body diagram, what's taking place at D, and I'm going to slide this up a little bit just to make so I can draw my free body diagram better. If I'm going to draw my free body diagram, my reaction forces are going to be like this. We can draw this vector here because there's not. It's going to equal 0 because there's no horizontal force. This does not cause a horizontal force. And the only other thing is you can tell that this guy is trying to cause it to rotate this way. So we're going to have a moment going back this way. And that's a moment at D. So, again, what you can do, you can create yourself another axis system if you want to. Oops, let me do it this way. Like this. Like this, and again, you can. Nothing says you can't. You could make this like x prime or y prime, or you could leave it x and y. It doesn't really matter. So again, you do the same thing here. You're going to sum the forces. I'll do a different color. If I sum my forces at D in the x prime direction, I have none. Along x prime, this does not cause any, so all I can say, we'll make this f dx prime, that f dx prime is equal to 0, because there's nothing to add it to. If I sum my forces in D in the y prime direction, I will get minus 120 coming down, plus f dy. We'll call this f dy is equal to 0. F dy would have to be pushing up. So f dy would equal to 120 newtons going up. And then the only other thing, again, sum the moments at D, and you would get 120 newtons. Let me go back to the picture and see what the distance is. Perpendicular distance from the 120 to D, and that is going to be 300. And make sure when you do this that when you do moments, it's always the perpendicular distance from the force, and then you'd have plus f dy, or excuse me, plus the moment at dy would equal 0. When I do that in my calculator, 120 times 300, and we should technically change that back to millimeters. So 300 divided by 1,000 times 120. I'll just check these numbers real quick. Yeah, that should be right. And that gives me a moment of 36 Newton meters. So scroll down, m dy would equal to 36 Newton meters, and it's going back that direction. And that's it. So I hope this video helps you. Again, keep things simple. Draw free body diagrams of each member, not of the system. Alright? Best of luck.